Dear ladies and gentlemen, I am Krisztián Lengyel from Budapest, from the Wigner Research Center for Physics from Hungary. I will speak about the cooperative luminescence of ytterbium pairs and saturation of the absorption of ytterbium ions in ytterbium-doped lithium-yttrium borate single crystals. First, I will speak about the lithium-yttrium borate crystals. Then I will show you the huge absorption of ytterbium ions in this host. Then I will show you how to measure the cooperative luminescence of ytterbium ions in lib ytterbium single crystals using continuous wave laser excitations. And after that, I will show you the temperature dependence of the spectra and the effect of the laser intensity to the spectra. After that, I will show you the model which we utilized to understand the effect. Dear ladies and gentlemen, I am Krisztián Lengyel from Budapest, from the Wigner Research Center for Physics. I will speak about the cooperative luminescence of ytterbium pairs and saturation of the absorption of ytterbium ions in lithium-yttrium borate crystals. First, I will show you the lithium-yttrium borate crystals, the physical properties and the growth technique. After that, I will present the absorption spectra of the ytterbium ions in lip crystals, and I will demonstrate the huge absorption of these ions in this host. After this, I show you the measurement of the cooperative luminescence of ytterbium ions in lithium-yttrium borate crystals using continuous wave laser excitations, and also the temperature dependence and the laser intensity dependence of the CL spectra. To understand the experimental results, I will demonstrate a model which based on the relationship between the ytterbium pair emission and the single ion absorption. The lithium-yttrium borate crystal has monoclinic structure similarly to all lithium rare earth borate crystal. Because of this similarity, the lithium-yttrium borate crystal can be doped any number of ytterbium ions. Usually, these borate crystals has excellent nonlinear optical properties with a wide ultraviolet transmittance range. So these kind of crystals are very good candidates for laser hosts and scintillation applications due to its flexibility and the easy incorporation of rare earth dopants at the yttrium sites. We usually grow the lithium-yttrium borate crystals by the Czochralski method, and this crystal has a melting point about 880 degrees centigrade. We measured the 0.1 and 20 more percent ytterbium doped lithium-yttrium borate crystals. It's very important that in the lattice the yttrium ions formed a chain, and in the chain the neighboring yttrium ions has a distance only 3.85 angstrom. And between the chains, the distance is much higher. It's 7.2 angstrom and 6.6 angstrom. This distance, this 3.85 angstrom, make the possibility to generate ytterbium pair emissions in this host. First, speak about the absorption of the ytterbium ions in this host. Here you can see absorption spectra of the ytterbium ions, which was measured at low only 8 Kelvin. The main absorption band, which is the narrowest from these three absorption bands has a very big amplitude at low temperature. However, this absorption band also shows a very big dependence as a function of the temperature, which is demonstrated here. At low temperature, the very narrow band means that only 0.16 reciprocal centimeter is the half-width of the absorption band, which can be measured only with a very thin sample doped with only a small quantity of ytterbium ion. Because here you can see that the absorption coefficient is 20, which is very high. Here you can see the temperature dependence of the maximum of the absorption coefficient and the half-width of this absorption band. Both are changed 2 order of magnitudes from 8 Kelvin to 300 Kelvin. The cooperative luminescence is a known effect from the 70s, which can be seen here, and here is one of the oldest figure where they found this ytterbium pairs emission in ytterbium phosphate crystal. It is the theory of the ytterbium pair emission is that if two neighboring ytterbium ions are in excited state, then they can relax together. They can relax together and emit one single photon with double energy. So that means that the photon which is emitted has 485 nanometer wavelengths. Usually the emission of this kind of photons has a quadratic intensity dependence, but in the literature we found that they measured 1.87 or a lot of type of exponents from 1.6 up to 2 values. In our measurement, we used a titanium sapphire laser, a continuous wave laser, which intensity can be changed from 5 or 0 up to 470 milliwatt. And we measured our spectra with excitation wavelengths at 972.3 nanometer, and the spot diameter at the sample was 150 micrometer. The emission was recorded by a spectrography CCD camera with a spectral resolution of 0.4 nanometer. The two spectra, as an example, are shown here. The spectrum measured at room temperature is a wide without a Brio structure, while the spectrum measured at low temperature shows a very detailed structure with a lot of bands. But if we try to identify the bands, then we recognized that the sum of the bands is came from an impurity, the dysprosium ions. But the other bands, which are real cooperative luminescence bands, can be marked as a combination of the single ion relaxation. The highest energy band is the double of the highest single ion transition from the ground level of the excited level. to the ground level of to the lowest level of the ground level. And we can assign these combinations, and more or less all of the bands we found these combinations. After that, we check the temperature dependence of this absorption of this cooperative luminescence spectra, and we can see that the bands where we can find also dysprosium bands and the ytterbium cooperative luminescence bands has different temperature dependence as the clearly ytterbium cooperative luminescence bands. So for the after the measurements, for the fit process, we just use this part of the spectra. So the integrated intensity was calculated from these wave numbers only. The laser excitation intensity dependence, we recognize that the emission spectra seems to be the same with the intensity of the laser, just the absolute value of the spectra is changing. And if we check one temperature and we plot the integrated area versus the laser intensity, then we can see that we have a power function, and here with an exponent 1.7. So we recognize that in different temperatures we have exponent values from 1 to up to 10 when the temperature changes from up to 300 Kelvin. So after these measurement results, we think about the reason of this interesting effect, and we have an idea that maybe the saturation of the absorption somehow can relate it to the different exponents. The saturation of absorption means that under intense continuous wave laser excitation, the number of the ytterbium centers available for absorption in the ground state significantly decreases when the excitation intensity exceeds a saturation threshold, so-called saturation intensity. And if we are in this regime, then the saturation absorption theory has to be used. This can be read in details in this article, which is now in print. So the basic assumption of this model was that there is a connection between the local absorption and the local population of the ytterbium ions in the ground and excited state, and also there is a relationship between the local intensity of laser light and the local population of the ytterbium ions in the ground and the excited states. So this equation is about the absorption values and the population, and this equation is about the population and the laser intensity. This can be found in this article as. After that, we have to solve the equation of light propagation in this absorption material near the saturation intensities. So that means that the equation of light propagation, the absorption coefficient changing with the intensity, and for the cooperative luminescence intensity, we have to calculate this integration, which can be done using this equation, and we get a function, which can be seen here, which in this equation we can see that there is the intensity 0, which is the illuminated laser intensity. The intensity D is the intensity at the exit side of the sample, and these are geometric constants, and the ytterbium ion concentration. This is the absorption coefficient, and ESAT is the saturation intensity. It's much easier to work with an assumption than we neglect the intensity at the exit side of the sample, which can be done because our sample absorbing very hard. So in that case, we get a function where we have a linear and a logarithmic part. And if we check the two cases when the saturation intensity is very small, which means that the absorption is very high, so at low temperatures, then we get a linear function as a function of the laser excitation laser intensity, and the large saturation intensities we got a quadratic function. So we have a solution which at low temperature which shows linear, high temperature shows quadratic, so it seems to be okay for our measurement results. So I made a simultaneous fit all of the measurement points together, where I have one common parameter, which is a geometry parameter, and 10 unique saturation intensity parameters. So every temperature I got one saturation intensity values. So we can see that the fit is very good, and at low temperature there is this linear function, while at higher temperatures more and more quadratic. And when we plot the saturation intensities which we got from the fitting procedure, then we realize that at the saturation intensity at room temperature, we have a value which is 11 kilowatt per square centimeter, which is very near to the literature value of 7.5 kilowatt per square centimeter, which was found here in this article. There is an independent way how to check the model quality, because there is a sub-relationship between the saturation intensity, the absorption cross-section, and the emission cross-section. If we put these functions together, then we can get a function to the absorption cross-section multiply saturation intensity has an exponential function, and when we plot this multiplying the absorption cross-section and the saturation intensity, and we made a fit with this function, we get a very good fitting, and we get only one parameter because we make the fit after the normalization at the low temperature measurement, and we get this parameter, and it shows that our model, from which we got these values, has a very good quality to describe this effect. So the conclusion that upconversion luminescence was investigated in lithium-yttrium borate single crystal doped with 20 more percent ytterbium under continuous wave laser excitation in the main absorption band of the single ytterbium ions at 972.3 nanometer in a very wide temperature range from 6 to 300 Kelvin. The upconversion luminescence was found to be featureless at room temperature, but it demonstrates a pronounced sequence of lines at low temperatures. Through the temperature region where we investigated the sample, the intensity of the cooperative luminescence could be described by a power function dependence on the exciting laser intensity, whereas the value of the exponent decreased with cooling. Based on the saturation absorption theory, a model describing temperature and laser power dependencies of cooperative luminescence intensity was developed, and the model was simultaneously fitted to all measurement data using only 11 parameters, resulting consequent saturation intensity values. And also the temperature dependence of the product of the absorption coefficient and the calculated saturation intensity can be satisfactorily fitted with a theoretical function, which can be considered as an additional validation of the physical background of our saturation intensity model. So thanks for your attention, and thanks for the cooperation project of the Estonian and Hungarian Academy of Sciences, and also the National Research Development and Innovation Fund of Hungary within the Quantum Technology National Excellence Program. Thanks again for your attention.